site on Earth. The idea of launching satellites from the ocean is not without its critics. As the company gets up and running, international concerns about environmental impacts, safety, and technology sharing threaten to block the operation before it gets off the ground. But the advantages of launching from the equator will result in big savings for satellite operators. Geosynchronous satellites launched from other latitudes must use their own precious fuel reserves to nudge themselves into position over the equator. But those launched from the equator have a straight shot and can use that extra fuel to stay in orbit longer. When satellites run out of fuel, they become useless hunks of orbiting junk. Their average lifespan is 10 to 15 years. The fuel saved by launching satellites from equatorial waters extends that life an average of 3 years. To the companies that pay hundreds of millions of dollars to have satellites built and launched, that's huge. However, the equatorial launch site raises environmental and safety concerns from fishermen on widely scattered South Pacific islands. The islanders fear that fuel slicks and emissions from the rockets will harm the fish that provide their livelihood. But the project uses the Zenit rocket, fueled by kerosene. Unlike other rocket fuels, kerosene is clean-burning and dissipates quickly in water. In addition, Sea Launch agrees to monitor water quality, install cameras to watch for endangered marine life, and institute a warning system to clear the area of fishermen before takeoff. Sea Launch is keen to clear hurdles quickly in an industry that has grown to nearly $100 billion a year. A commercial boom, born of two major events in two countries. First, America's 1986 Challenger explosion puts an end to the use of manned space shuttles to launch commercial satellites.
We have main engine start, 4, 3...
Prior to the Challenger disaster, NASA had a monopoly on commercial satellite launches in the US. With the shuttle program indefinitely suspended, the lucrative and growing private launch business is up for grabs.
Engines beginning throttling down now.
Then, the fall of the Soviet Union in 1991 ends that government's stranglehold on space technology. In a fledgling free market economy, private Soviet rocket companies begin to ply their wares. Both of these events create new opportunities for private sector ventures into space. The worldwide satellite launching market is dominated by 4 major players. Baikonur Cosmodrome in Russia, Cape Canaveral, and Vandenberg Air Force Base in the US, and Ariane Space in French Guiana. There are also smaller launch facilities in India, Japan, and Russia. All are land-based. In 1993, an international group of aerospace firms, headed by Boeing, begins looking for a way to challenge the industry giants. To challenge the established land-based competition, the consortium will pursue a bold new strategy to deliver increasingly large commercial satellite payloads into orbit at a lower cost. They will attempt to build an ocean-based system that can launch satellites from the equator. The task is monumental. In the time it takes to build an ordinary cruise ship, the team must construct two megastructures: a one-of-a-kind mission control ship and a floating launch pad that can withstand the fiery force of a rocket launch. Hardest of all, these former rivals must find a way to work together without giving away military secrets or violating corporate and governmental regulations. And all of this must be done under the pressure of a seemingly impossible deadline. If they succeed, the megastructures they create may change the commercial satellite launching industry forever. In concept, building a seagoing megastructure that can launch satellites into geosynchronous orbit from the equator is a brilliant plan. The aerospace expert who will lead the effort is Bo Beamock. Beamock helped get NASA's Space Shuttle and International Space Station off the ground. Yet his new challenge is even more daunting.
Working on sea launch, that's the most fun project I've ever been involved with. There's no question about it. But it was also probably the most difficult thing I've ever done.
The difficulties start with engineering a seaborne system that can endure 730 tons of rocket thrust without sinking the ship or cooking the crew. To get an idea of that kind of thrust, picture 14 of the world's biggest commercial jet engines bundled together and firing at maximum power instantaneously. Not your average takeoff. To survive the blast, the crew needs to be 5 kilometers away from the rocket launch. Problem is, they're in the middle of the ocean. So, what's the solution? 2 separate vessels. One, called Odyssey, will be a gigantic floating launch pad. The other, a ship called Commander, will be a remote mission control. At launch time, the Commander, with the crew aboard, will position itself 5 kilometers away from Odyssey's launch pad. But a 2-ship system leads to a multitude of other problems. First, designers will need a way to get the crew off the Odyssey prior to launch. Not an easy or safe task in the open ocean. Then, once evacuated, Odyssey must automatically go through all the operations necessary to launch a rocket, without a soul on board. Designing Commander, the mission control ship, has its own challenges. It needs an automated launch facility and 2 helms, one to run its own machinery and one to remotely operate the machinery aboard Odyssey. The plans for Commander also include a rocket assembly plant with room for 3 60-meter-long rockets. In this floating rocket factory, crews can constantly process payloads for upcoming launches. In December 1995, Sea Launch's Norwegian partner, Kvaerner Boatbuilding Company, begins work on Commander in their Glasgow, Scotland shipyard. The shipbuilding giant quickly realizes that even with their experience building specialty vessels, they've never built anything like this. Commander will stretch 200 meters, almost 2 American football fields, and will be over 33 meters wide. It will be the only non-military vessel in the world with completely assembled rockets in its hold. And it will also be the only ship in the world with the ability to launch those rockets by remote control. Unique, too, is the international partnership at work on Commander. The shipbuilder is Norwegian. The shipyard is in Scotland. The satellite technology and mission management are mostly American. But the rockets are Ukrainian and Russian. And that's where the project hits its first roadblock.
Some of the information was still embedded in Russian military secrets.
Not only are their defense secrets at risk, but government regulations also forbid the sharing of technology that could be used to build weapons of mass destruction. This means the Russians and Ukrainians cannot share details of their top-secret rocket technology with the shipbuilders. So, if creating two enormous structures stable and strong enough to exist out at sea isn't complex enough, the regulations mean that Kvaerner can build only the infrastructure of Commander. The rocket assembly fittings will have to be added later in Russia. So the Norwegian shipbuilders lay the vast foundation of metal and machinery for Commander's two unique functions. On the main deck within the hold, a vast space is reserved for rockets. At the stern end of the upper deck, a compartment is created for mission control. One design issue has everyone stumped. Commander must have the capability to evacuate the crew of the launch platform Odyssey before the fiery blast of liftoff. Doing that quickly, safely, and dependably in the open sea will require a retractable metal bridge linking the two vessels. But putting two ships that close together in the open ocean is a dangerous proposition. Currents or waves could grind the vessels together, causing massive damage to the ships and jeopardizing the lives of crew members crossing the bridge. To stabilize the ship during evacuation, Kvaerner adds what's known as an azimuth thruster. Coupled with a dynamic positioning system, the extra thruster helps keep the ship steady while platform workers maneuver across the link bridge. For the other half of the two-ship operation, designers needed to find a vessel that could be transformed into the launch platform that would be dubbed Odyssey.
We started
to look at major ships that could carry a lot of tonnage. That could have been oil tankers, or ships to transport dry cargo, or former military ships, including submarines.
But none of these options provide exactly what's needed. Finally, after an exhaustive search, a possible candidate is found rusting away on a maritime scrap heap. This Japanese-built oil rig drilled in the North Sea until a deadly fire decommissioned it in 1988. The burned-out platform has the basic structure sea launch needs, but it will take massive modifications to transform it into a floating rocket launcher. The derelict platform is towed to Rosenberg shipyard in Stavanger, Norway, and Kvaerner engineers get to work. During takeoff, 730 tons of rocket thrust will pound Odyssey's deck. So job one is making the platform rocket-proof. To deflect the explosive force of liftoff, thousands of tons of high-grade structural steel are added to the platform. Two more massive steel legs are added to support the 15-meter deck extension that will become the launch pad. To stabilize the immense platform, Its mammoth legs are made so they can sink during launches, and the pair of pontoons supporting the base are lengthened. The pontoons are dwarfed by the megastructure that sits atop them. To get a sense of scale, compare the size of the pontoon to the size of a Seawolf nuclear attack sub. The pontoon beats the Seawolf by over 25 meters. When complete, this vessel will be 67 meters wide and 133 meters long. One of the largest self-propelled semi-submersible vessels in the world. The strategy is in place to create these two maritime megastructures. Now, the world waits to see if this vision can truly become a reality. July 1996. And as the work to convert Odyssey from a burned-out oil rig continues, the focus turns to power. This colossal rig will need the means to get itself to its equatorial launch site. No tugs, no tows. So a massive power plant is installed. 4 direct current electric motors will turn the 4 2.5-meter props to push this beast through the world's oceans. Once it arrives at its launch site, Odyssey will need a way to maintain its position on the equator. With the ocean floor 4 kilometers below, dropping anchors isn't an option. Instead, Caverna installs a dynamic positioning system. Engines and thrusters are connected to a computerized global positioning system, or GPS. When Odyssey moves from its fixed position, the GPS system automatically steers it back into place. Another dilemma engineers face is rolling out and lifting 60-meter rockets on a deck that's too short for the job. Here's the problem. The rockets must ride horizontally to the launch site in hangars on Odyssey's deck. Then, each rocket must be rolled out of the hangar horizontally and lifted to a vertical position on the launch pad. This means the pad has to be at least twice the length of the rocket. But Odyssey's deck is significantly shorter than that, and adding that length would be both a costly and unseaworthy proposition. Some out-of-the-box thinking solves the problem.
We actually sort of cheated a little bit because we made a big notch in the hangar door so that we don't have to have twice the length of the rocket. We would roll it out fully, and then the rocket would be lifted through that notch in the ceiling of the hangar.
The final design challenge of the launch platform superstructure is the launch pad itself. A solid surface would deflect the rocket's blast sideways, damaging crew quarters, the rocket hangar, possibly even the control systems of the launch platform. Engineers solve the problem by utilizing something this launch site will have in abundance: water. The spot where the rocket takes off from the deck isn't solid. It has huge vents. The hot rocket exhaust will blast down through these vents, and the energy will be absorbed by the water below. The innovation is more launch bucket than pad. In May 1997 in Stavanger, Norway, Odyssey's retrofit is complete. The transformation is astounding. Now, instead of drilling for oil, this rig will attempt to drill rockets into space. Four months later, in the Glasgow, Scotland shipyard, Odyssey's counterpart, Commander, is christened. The ship that will serve as a rocket assembly plant and mission control goes from concept to launch in under 2 years. The Norwegian shipbuilders have been exceptionally fast, and they celebrate accordingly. But despite the celebration, both Commander and Odyssey are far from finished. Both must now be fitted for the Soviet-era rockets they will carry and launch. This is when the construction enters its most technically challenging phase, turning these ships into rocket ships. Commander and Odyssey must now set sail separately for shipyards near St. Petersburg, Russia. This is where Sea Launch's Russian partners will do what's never been done before: pack an entire satellite launch system onto the two ships. Everything from fueling systems to the remote rocket launching controls will be installed on the ships. Laborers must toil around the clock to meet the deadline. The ships employ more than 1,000 Russians and Ukrainians, a welcome boon to Russia's shaky post-communist economy. 540 tons of electronic and mechanical support systems for mission control are installed on Commander, transforming it into a floating Cape Canaveral. Rocket handling equipment goes into the massive hangar, while the control room gets computerized launch systems. Helm controls are added to enable mission control aboard Commander to remotely control operations on Odyssey's launch pad. And again, because of those restrictive technology sharing regulations, a customized control room is constructed to separate the Russians from the Americans. Odyssey, the launch platform, goes through an even more radical renovation. 2,700 tons of automated rocket handling equipment are added to the gargantuan launch platform. Transporters, fuel systems, a launch area. All must be perfectly calibrated to handle rocket launches.
Okay, this is autocoupler. That's how it goes.
June 1998, and the St. Petersburg crews complete the retrofit of both vessels on schedule. Commander and Odyssey leave Russia bound for Sea Launch's home port in Long Beach, California. Although they have the same destination, the size difference between Odyssey and Commander forces them to travel in opposite directions to get there. Commander, just over 32 meters wide, barely makes it through the Panama Canal with only a couple of meters to spare. The tight squeeze allows Commander to take the shortcut to the Pacific. But Odyssey, more than twice as wide at 67 meters, is far too big for Panama. Instead, the reconditioned oil rig travels a route that cruise ships would envy: into the Straits of Gibraltar, the Mediterranean Sea, and through the much wider Suez Canal. This is likely the first and only time a 10-legged rocket launcher will pass through this canal. July 1998, and after a 31-day journey at sea, Commander arrives at home port in Long Beach, California. Then, another 83 days later, the mammoth megastructure Odyssey makes its spectacular entrance.
Still, I have the clear picture of platform arrival. Captain kept calling. They were about 30 30 miles offshore from the home port. And I remember looking at this, and it was surprising. It looked different than I expected. It looked like a white ghost, almost immobile. And I was thinking, my God, we made it.
Over 50,000 tons of steel sit tied to the pier at Long Beach, poised to penetrate space. But the big question for this megastructure still lies ahead. Will this enormously complex mission succeed? Can these vessels sail to the middle of the Pacific Ocean and perform a perfect launch from the equator? In March 1999, the world's first two-vessel rocket launcher is ready to embark on its maiden mission. The builders of Commander and Odyssey have leapt complex technological hurdles in record time. Now, it's time to test this megastructure's mettle. After an 11-day expedition from their home port in Long Beach, California, Commander and Odyssey reach their destination at the equator. As the Odyssey straddles the equator, the dynamic positioning system is holding it steady at 0 degrees latitude, 154 degrees west longitude. This all-important debut launch will feature a satellite called Demosat. This payload mimics the size and weight of a real satellite. The major difference, it doesn't have an anxious paying client attached to it. At 3 hours before launch time, with all systems in place, every member of the launch pad crew evacuates Odyssey across a steel gangplank extended from Commander. In mid-ocean, the two enormous vessels become one. For those making the crossing, it's a heart-pounding moment, especially when the gangplank sways.
Yeah, I was a little nervous the first time because it moves back and forth and goes up and down. It's designed in an emergency situation to release, but it'll give you a 30-second alarm. So you have 30 seconds to decide which end you want to run to.
With Odyssey's crew safely aboard, Commander puts 5 kilometers between itself and the launch pad. On the abandoned Odyssey, the Virgin launch is now in the hands of an automated system. Fuel flows into the rocket from huge pipes at the bottom of the launch pad. Once fully fueled, the rocket will weigh nearly 500,000 kilograms. The transporter erector tucks itself back into the hangar. Hangar doors close, protecting the valuable equipment inside from the rocket's blast. 5 years of incredibly hard work is about to reach a fiery climax. Demosat is lifted from its ocean-going launch pad on the equator to geosynchronous orbit 35,900 kilometers straight up. The first launch is a success.
You know, the whole business is at stake on a launch. And to see it lift off and to see it go through the operation is just an incredible defining moment.
Seven months later, in October 1999, Sea Launch follows this perfect test launch with its first official launch. The 3,400-kilogram direct-TV satellite becomes the first commercial satellite launched from sea. The concept is proved. The technology works. After knocking its first 2 satellites out of the park and into orbit, Sea Launch enters the new millennium with 18 launches on its manifest. But its perfect launch record is about to be broken. 5% of all satellites launched don't make it to orbit. The odds quickly catch up with Sea Launch during its 3rd mission. In March of 2000, the company launches a $100 million communication satellite for a London-based company. It's a picture-perfect launch. Then, 8 minutes into the flight, radio contact is lost, and the rocket plunges into the Pacific. After 2 months of exhaustive investigation, the failure is tracked to a software problem. The automatic system didn't close a fuel valve on the 2nd stage rocket. The 2nd stage engine shut down too early, and the launch self-destructed, as it is designed to do when a fatal flaw occurs.
And in fact, I think if you weren't afraid of the risk, you're probably in the wrong business.
Investigating the failure costs the company precious time. But the software problem that caused the crash is fixed. By the end of July 2000, Commander and Odyssey are back at sea, hurling another rocket into space. 1 hour and 37 minutes after liftoff, Pan Am Satellite 9 is in geosynchronous orbit above the Earth. In October of 2000, there's another milestone. Sea Launch breaks the world record for heaviest commercial payload when it effortlessly tosses a 5,100 kilogram communication satellite into orbit. This mega-heavy launch proves that the Sea Launch equation works. In the next 4 years, Sea Launch successfully puts 8 more commercial satellites into geosynchronous orbit above the Earth. A dazzling string of achievements for this seafaring launch pad. But as the Sea Launch team revels in their success, the odds catch up with them once again in June of 2004. The Telstar 18 satellite launch experiences a malfunction. The 3rd stage rocket delivers the satellite to a lower altitude than expected. Then, in December of 2004, the launch of Intelsat Americas 8 was called off, cancelled at the 11th hour by the client because of potential problems with the satellite. These back-to-back mishaps put enormous pressure on the first launch of 2005, Mission 15. If this launch is a failure, the entire operation could be at risk. The future of ocean-based satellite launches rests on this next mission. With only 3 successful launches in 2004, the international team needs Mission 15 to be a hit. It's more than a launch. It's a shot at success. With a puff of smoke from the stack and a nudge from a tug, the mighty Odyssey is underway. With a 4.5-ton, $250 million payload. The speedier Commander leaves port 4 days after Odyssey. After 11 days at sea, Odyssey and Commander are reunited at the equator, and preparations for the launch begin. The crew of Odyssey then does something remarkable. They sink their ship, partially. As with every liftoff, 6 underwater valves are opened in the pontoons, and Odyssey's legs take on thousands of litres of water. The platform sinks to a depth of approximately 22 metres, making it stable for launch. A dynamic positioning system acts like an anchor, holding the platform in place. But on this mission, Mother Nature trumps technology. Strong ocean currents overpower the positioning system, and the platform isn't steady enough for launch. The countdown is put on hold. The next day, equatorial currents continue to push the platform around. Launch still isn't possible, and the rocket is returned to the shelter of the hangar. The postponement stretches to almost a week as Sea Launch waits for the currents to let up. Finally, on February the 22nd, conditions are perfect for launch. 3 hours before liftoff, Odyssey's crew evacuates across the narrow steel bridge. They join the crew of Commander and steam 5 kilometers upwind of the launch pad, a safe distance should anything go wrong with the rocket. Aboard Odyssey, automated systems commence fueling the rocket without a single human aboard. Five kilometers away, aboard Commander, the American and Russian crews of Mission Control monitor every aspect of the launch. They carefully watch data on weather, currents, fueling systems, the satellite environment, and endless other details.
We like to say that there's not too many people are breathing in the last 3 minutes.
Anything can go wrong. And as the countdown enters the last tense minutes, something does. A problem crops up during a pre-flight check, and the automatic launch sequence shuts down. The launch was aborted due to a problem with the Ukrainian-built Zenit rocket. Ukrainian scientists huddle to solve the problem without further explanation. One thing is certain: if the launch hadn't automatically shut down, the rocket would have failed in flight. Finally, on February the 28th, 6 days after the aborted launch and 26 days into their mission, the engineers are ready to try again. The rocket emerges from its hangar, and the hydraulic arms of the transporter erector push it into ready position. If this countdown doesn't end in a launch, both vessels will have to return to port with Mission 15 still incomplete. 3 troubled missions in a row would be a devastating blow. Tension is in the air as the crew watches the rocket prepare, and the screens flash. What looks like steam coming from the rocket is actually liquid oxygen discharge, a normal byproduct of fueling. Clocks keep count until the last 10 seconds.
10, 9.
The count from 10 is the only countdown in the world done in both English and Russian.
Main engine start coming. 2, 1. Lift up. Main engine is at nominal thrust.
Mission 15 liftoff is a success. As the rocket disappears from view, the most crucial elements of this launch are yet to come. They take place kilometers above the Earth. It will be an hour before the crew in the command center will know whether Mission 15 is successful. 2 minutes into the flight, about 70 kilometers above the Earth's surface, a spent Stage 1 successfully separates from the Ukrainian Zenit rocket and falls to the ocean. The engines on Stage 2 begin to burn, and the rocket slows down to a mere 9,600 kilometers per hour. A minute later, the fairing protecting the satellite at the tip of the rocket also falls away. Stage 2 burns for 6 minutes, then it too falls away. Now it's up to the Russian third stage, called the Block DM, to complete the satellite's journey. The rocket is now 180 kilometers up and 6,400 kilometers downrange. The third stage fires up for 2 longer burns and pushes the satellite from suborbital into orbital space above the Earth's surface. 1 hour after liftoff, the third stage separates. The satellite is on its own. Within minutes, a station in Africa reports receiving a test signal from the satellite. Mission 15 is a complete success.
I'm most proud of the team. I think we have the best launch team in the world, the best leadership team in the world. We're a private company doing what huge governments are having trouble doing.
The success of Mission 15 is followed by another triumph 2 months later. Mission 16 breaks Sea Launch's own world record for satellite weight and moves a step closer to the consortium's goal of 5 launches in 2005. The idea that came from science fiction is leaving naysayers in its wake. With each success, these mighty machines come closer to the day when ocean-based rocket launching will be routine. But there will never be anything routine about these incredible megastructures that link sea and space.
Lay down.